Thank you very much for kind introduction and for having me here today to present my work. I hope everyone can hear me well, also people online. So today I will talk about my project titled Inference on Local Variable Importance Measures for Heterogeneous Treatment Effects. And this is joint work with Alex Lutke and Peter Gilbert. And please feel free to stop me anytime, especially if there will be some clarifying questions. Okay, so in high-risk domains, for example, in medicine, decision makers may hesitate to rely on the black box decision support systems without understanding the rationale behind the recommendations. So goal of this work is to develop an inferential framework to assess variable importance, and especially in the context of heterogeneous treatment effects. The variable importance measures that I will discuss today are local in that they may differ across individuals, while the inference is global in that it tests whether a given variable is important for any individual. So for maybe those of you less familiar with variable importance literature, let me make a small remark. So one of the popular distinction that is being made in variable importance literature is between so-called algorithmic variable importance measures, where we may have in mind some kind of model, maybe based on neural networks or random forests. And then we would like to apply these variable importance measures to understand how given prediction model uses the information to make predictions. So these type of variable importance measures are called algorithmic variable importance measures. So on the other hand, there are so-called model agnostic variable importance measures where our interest is not in understanding particular prediction model, but we want to understand variable importance from the point of view of data generating process. And in the work I'll be presenting today, we will be looking at model agnostic variable importance measures. And model agnostic variable importance measures can be further divided into so-called global variable importance measures. So global variable importance measures are averaged across the whole population. So for example, when you think about ranking of importance of variables, that would be a single ranking of importance for the whole population. On the other hand, the local variable importance measures that we will consider today may provide different variable importance for different individuals. So in particular, different individuals may have different ranking of importance of a given variables. Okay, so let me move to problem setup. So we have vector of covariates X, which we assume to be sufficient for confounding adjustment of a binary treatment A on outcome Y. So the main object of interest will be conditional average treatment effect, or CATE, given by Formula 1. So this is just treatment effect conditional on some subset of patient covariates. So here YA denotes the potential outcome under treatment A, and S is some subset of indices of the covariates. So under causal assumption, which are often invoked in causal inference literature, that is of positivity, consistency, and conditional exchangeability, this conditional average treatment effect given by Formula 1 can be identified as a statistical estimate nu given by Formula 2. Okay, so given that we introduced this object of interest that is conditional average treatment effect, we may be interested in answering the question how to quantify the variable importance for Kate. So one of the popular classes of variable importance measures are so-called leave-out covariates or local variable importance measures. So leave-out covariates variable importance measure for Kate is defined through expression 3. So here we're trying to quantify importance of feature I. And we define this local variable importance measure of feature I for Kate as a difference of two Kate functions, where in one case we're conditioning on subset S of covariates plus feature I, of which importance we wish to quantify, minus Kate, where we're conditioning only on subset S of variables. So here we have some freedom in terms of choice of this subset of covariates S. So for example, if we set S to all covariates except of feature I, then the corresponding variable importance measure is called leave one out variable importance measure. Whereas if we set S to be an empty set, then the resulting variable importance measure is called keep one in variable importance measure. Okay, so now given that we define a candidate variable importance measure, we may be interested in testing the null hypothesis of zero importance of a given feature I. So here our null hypothesis is that gamma I, so our variable importance measure for feature I, is equal 0, P almost surely, against the alternative, not H null. So an initial idea how we would like to test it could be, for example, to consider a test statistic being squared norm of our variable importance measure gamma I. However, there is a problem with this approach, namely under null, the efficient influence function of this quantity is equal to 0. So efficient influence function is a first order approximation of our quantity of interest, which is often used for construction of estimators with good properties. So these object efficient influence functions are used for debiasing of the estimators to obtain estimators with better statistical properties. However, the problem that we are facing here is that under null, this efficient influence function, so this first order approximation, is equal to 0. So we cannot use that strategy. So as a result, potentially higher order parameter expansion would be needed to develop valid tests. However, here we're proposing alternative strategy to deal with this problem, namely to perform so-called reproducing kernel Hilbert space embedding. So let me provide a little bit of intuition what RKHS embedding is. So for a symmetric continuous positive semi-definite kernel function K, we can define RKHS embedding through formula 4. So these two graphs that I'm presenting, they provide a little bit of intuition what the RKHS embedding does. So the red curves correspond to our original functions, and blue curves correspond to their corresponding RKHS embeddings. So if we look at the graph on left-hand side, where the original red curve is fairly well behaved and smooth, then RKHS embedding doesn't change it much. On the other hand, when we look on the graph on the right-hand side, if we have function that is less well-behaved, much more wiggly, less smooth, then we get significant smoothing out effect through performing this RKHS embedding. And importantly, RKHS embedding is an injective mapping for an appropriate choice of the kernel. Okay, so now that we've introduced this RKHS embedding, we can define RKHS embedding of the local variable importance measure that we considered, which is given by formula 5. An important result that we will rely on later on is that this RKHS embedding of Kate function is pathwise differentiable and has this first order approximation that is efficient influence function. And as immediate consequence, since our local variable importance measure is just difference of two Kate function, also RKHS embedding of the local variable importance measure is pathwise differentiable and has efficient influence function. That is this first order approximation that we can use to construct estimators with good statistical properties. So one of the popular examples of such an estimator with good statistical properties that we can obtain using this object efficient influence function is one-step estimator. So one-step estimator of this RKHS embedding of our variable importance measure is given by this expression 6, and it has a usual form of one-step estimator. That is this plugin component of the estimator, and then this bias correction term, which is an average of efficient influence functions. And then we have the following weak convergence result for our one-step estimator. So this weak convergence result can be understood as an asymptotic normality result for our estimator. So given this weak convergence result given by expression 7, so this result allows us to perform statistical inference and in particular to construct valid statistical tests. Okay, so now we are well positioned to propose an equivalent statistical test of our null hypothesis of zero importance of a given feature. So now the null of our test is that the norm of this RKHS embedding of variable importance measure that we consider is equal to 0 against the alternative that it's different than 0. So one would reject the null if the norm of one-step estimator is larger than some threshold given by square root of this psi hat over n, where psi hat is 1 minus alpha quantile of squared norm of the limiting object in our weak convergence result. But the important fact about it is that we are able to approximate this quantity using bootstrap procedure. So this test asymptotically controls type 1 error at level alpha, and it has asymptotically non-zero power against local alternatives. Okay, so class of variable importance measures, so these local variable importance measures, they have some limitations, and let me just mention some of them. So for example, if two covariates xi and xj are highly correlated, then gamma I will typically be close to zero, potentially underestimating the importance of feature I. Further, these local variable importance measure do not capture interaction effects well. So for example, a given variable may appear unimportant alone, but be crucial in interaction with another feature. And another potential limitation is that this definition of local variable importance measures, as we have seen, rely on this potentially arbitrary choice of the subset of covariates S. And maybe we may wish to consider variable importance measures that do not encapsulate this kind of choice of subset of S. So therefore, we wanted to consider also other examples of variable importance measures. And a popular another example of variable importance measures are so-called Shapley values. So let me motivate a little bit where the idea of Shapley values comes from. So originally, the idea has been introduced in cooperative game theory. So cooperative game theory aims to distribute the payout among a group of cooperative players in a fair manner. So consider a cooperative game played by three players, A, B, and C. And as a result of this cooperative game, they obtain a total payout of $19. And now we wish to understand how to distribute this total payout among these three players in a way that acknowledges in a fair manner their individual contributions to the game. So Lloyd Shapley postulated that a fair payout allocation rule should satisfy the following set of axioms. So axiom of efficiency. So here the meaning of the word efficiency is different than commonly used in statistical literature. And here it means that sum of individual contributions shall sum up to the total payout. Furthermore, the axiom of symmetry, saying that the contributions of two players shall be the same if they contribute equally to all possible coalitions. Furthermore, axiom referred to as dummy, meaning that if a player does not contribute to any coalition, then they should receive zero contribution. And finally, the axiom of linearity, stating that if there are multiple games, then the total contribution of a player is the sum of contributions from different games. So Shapley value is a unique credit allocation procedure satisfying above axioms. And Shapley value for player I is given by the expression 8. So here omega is a payout function which take as an input subset of players and as an output provides the corresponding payout obtained by this group of players. Okay, so let's try to understand this formula a little bit better. So the crucial part here is this red part. So the difference of a payout obtained by group of players S plus player I, whose importance we try to understand, minus payout of group of players S playing without player I. So this difference provides us the marginal contribution of player I to this coalition of player S in terms of payout. And then to obtain the Shapley value of this player I, we're averaging over all possible choices of this coalition of players S. Okay, so let's try to understand these Shapley values a little bit better on the example on the bottom of the slide. So this picture illustrates, again, a game of 3 players, A, B, and C. And imagine we would like to compute the importance of player A. So we would like to compute the Shapley value for player A. For that, we would look at the payout obtained by player A playing alone minus payout obtained by empty coalition. Then we would look at the difference of payout obtained by players A, B playing together minus payout obtained by player B playing alone. Then we would look at the payout obtained by players A and C playing together minus payout obtained by player C playing alone. And finally, we would look at the payout obtained by players A, B, and C minus payout obtained by players B and C playing without player A. So in this way, we are quantifying the marginal contribution of player A to all possible subset of players. And now, averaging over all these marginal contributions, we're computing Shapley value of player A. So later, this idea of Shapley values has been adopted in machine learning literature to assess feature importance in prediction models. And here we're adapting this idea to compute the Shapley value of I feature for Kate. So the formula that we see on the slide, formula 9, is pretty much the same formula that we have seen before. Just instead of payout function, we're looking at the difference of 2 Kate functions. On one hand, conditional on subset S of variables plus feature I, in which importance we are interested, minus Kate function only conditional on subset S of variables. So another way of viewing these Shapley values, like especially when we look again at the red part of the expression. So this red part of the expression that we see is just local variable importance measure that we looked at before for particular choice of subset S of features. So another way of viewing these Shapley values is averaging these local variable importance measures over different choices of subset of covariates S. Okay, so going for a moment back to our example, now how it would look like in the context of Shapley values of I feature for Kate. So now this A, B, and C correspond to 3 covariates that we have at hand and which importance we would like to understand. And now let's say we wish to understand the importance of variable A for conditional average treatment effect. So for that, we would look at the difference of Kate conditional only on a single variable xi minus average treatment effect, then difference of Kate conditional on variables A and B minus Kate conditional on variable B, then Kate conditional on variables A and C minus Kate conditional on feature C, and finally Kate conditional on variables A, B, and C minus Kate conditional only on variables B and C. And again, looking at all these differences and averaging all these differences, we obtain Shapley value for variable xa. Okay, so let me now talk about some results of the simulations. So in this simulation setup, we were interested in testing zero importance of feature x1 in our simulation setup. So here I'm presenting the results for three variable importance measures that I discussed before. So in the first two rows, present the results of two local variable importance measures. So leave one out and keep one in variable importance measures. And the bottom row presents results for Shapley values. And then in first column, I'm presenting results under null setup. And in the second and third columns under smooth and rough alternatives. So simulation scenarios that I'm presenting here are indexed by two parameters. One is parameter beta, which quantifies the importance of feature x1, whose importance we are testing here. In particular, the setups of beta equal to 0 corresponds to the null scenario, whereas beta's non-zero corresponds to alternative scenarios. And then the second parameter, sigma, quantifies the pairwise correlation between covariates in our simulation setup. So two main takeaway messages from these simulation results is that under null, the test that we are proposing controls type 1 error at level alpha, even though our procedure is conservative. And the second point would be that as the sample size grows, then the power of our test goes to 1. Okay, let me also talk about the empirical example in our study. So we considered a global phase 3 randomized placebo control efficacy trial of Sanofi's bivalent SARS-CoV-2 recombinant protein vaccines with GSK ASO3 adjuvant. And the trial has been conducted among adults aged 18 and older. So vaccinations or placebo were administered on day 1 and day 22. The study was conducted in two stages. Stage 1 assessed a monovalent vaccine containing the original D614 SARS-CoV-2 spike protein, and stage 2 evaluate a bivalent formulation, including both D614 and the beta SARS-CoV-2 spike protein. And stage 2 of the trial enrolled 13,000 participants between October 21 and February 22. So our analysis focuses on the per protocol stage 2, that a cohort that had evidence of previous SARS-CoV-2 infection at enrollment. And it consisted, so the data set includes almost 600 individuals from Ghana, Honduras, India, Japan, Mexico, and the US. So in our data set, we have 305 individuals assigned to the vaccine and 292 individuals assigned to placebo group. So among baseline covariates, we have information on demographic factors. So for example, age, sex, BMI, and country. And two immunological markers, that is baseline neutralizing antibody titer against BA1 strain and concentration of binding antibodies against the Omicron strain. And the objective here is to try to answer the question, like how baseline characteristics influence the effect of COVID-19 vaccination on an immunological outcome, which here is neutralizing antibody titer against the BA1 strain of SARS-CoV-2 measured at day 43. So these are results of our analysis. And again, I'm presenting the results for 3 variable importance measures that I introduced before. That is keep one in, leave one out, and Shapley value. And I guess the main interesting takeaways is that 2 of the covariates, that is country indicator, and one of the biomarkers that is neutralizing antibody titer against BA1 strain. 2 of the variable importance measures that we consider, that is Shapley value and keep one in variable importance measure, suggest non-zero importance for these variables. Okay, so to summarize, we present an inferential framework for evaluating variable importance in the context of heterogeneous treatment effects. We provide efficient estimator of this measure together with corresponding confidence band. So that's the part I haven't talked today about. And we also introduced a wall type test to assess the null hypothesis of zero importance of a given variable. And as mentioned at the beginning, our approach focuses on local variable importance measure that may vary among individuals, coupled with global inference that assesses the overall significance of a variable across all individuals. So here are some selected references. And thank you very much for your attention. And I would like to acknowledge support of Pacific Institute for the Mathematical Sciences and eScience Institute at the University of Washington. And yeah, I would be happy to take questions or the discussion.